Hello, today we are going to do a quick recap of some of the things we know from junior cycle area type questions, and we are going to look at something that might be a little bit new in terms of the trapezium and polygons, both of which you may have come across before, but we're going to cover anyway just to be sure. So the advice that you would have gotten in junior cycle still stands. Whenever you get problems involving areas, you often need to break those shapes that you're given, those situations you're given, into shapes that you have formulas for, that we have equations for. And those equations are going to be found on page 8 and 9 in your log tables or your equations tables for the most part. And that is what we need to approach these questions as. We look at the questions, we say, well, let's open up page 8 and 9 in our books and see if we have any tools available to us that are going to help us to solve this. And can I recognize how I can break down the shape I've been given into shapes that I have formulas for? That's the real core skill of these types of questions, because the formulas we get used to fairly quickly. Now, a formula we haven't had too much time with before is the trapezium formula. This formula is going to become very important at the end of the chapter. We're going to use it to find the area of complex shapes at the end of our chapter. And for now, we are just going to look at it as an isolated shape. And the key thing about a trapezium is that it has two parallel sides, and then the other two sides are just straight lines. So we have two straight parallel sides, and then the other two sides can do whatever they want. And it has a particular height which we measure between the parallel sides, and the formula for its area is given by a plus b. So the two parallel sides lengths added together divided by 2, so the average of our two parallel sides multiplied by the height, which is given as the distance between our two parallel sides. And that's all the trapezium is. So if we have a look at a formula, if we look at applying the formula here, we have a trapezium. So I have these two written in. You'll often be expected to judge that these are parallel sides as opposed to them actually bothering to put in the parallel markers, the little arrows that tell you that the lines are technically parallel. So if they look very much parallel, this is one of the cases where you can judge that they are. They won't give you something that's slightly off to confuse you in this case. So in this case, we're given something we recognize as a trapezium. There's two parallel sides and the other two sides are going off doing something different. And we're given the area, we're given the two parallel side lengths, and we're asked to find the height. So what I'm going to do is go to my diagram that I'm given, and I'm going to draw in the thing I am looking for. So I can draw in the height in a bunch of different ways, like I did up here. I could draw it outside, or I could draw it in here. And it would again be the same height here. And you can see that you might break this up into two triangles and a rectangle under certain circumstances. We don't need to do that here. Now, what we do need, now that we've drawn in our diagram and we know what we're looking for, is to go to our log tables and to write down our trapezium area formula, because we're given information on the area. So we're going to write down the area formula. If we're given information on the area, we write down the area formula, whether we know how to continue or not. Then let's sub into this formula and see if we end up with an equation with only one unknown. So we end up with 50 is equal to a plus b to on h, and lo and behold, I have an equation that only involves h that I'm now able to solve to get h is 5, and I look to my question and I see I have h is 5 in centimeters. And that's how I approach these questions. If I see a shape, I'm going to write down the formulas connected to that shape. And once I've subbed in the information I've been given, once I fill in my diagram as much as I can and sub in the information I've been given into the formulas that are relevant to that shape, almost always I will be able to make progress. And that's the training we need. If we see something that's a little bit funny, I can say, well, I know a formula for that. Let's sub into that formula and see if we can make progress from there. Now, another example is here. We have a right angle triangle and we're given this shaded in area here. We're asked to find the area of the shaded region. What do I recognize this as? Well, I'm pretty certain that it is going to be a parallelogram. There's a few different ways that I can judge that it must be a parallelogram. It looks basically like one, and they're unlikely to give you something that's this close to a parallelogram just to trick you. But how could we justify it? Well, we can see that our lengths here, this length is equal to this length. We've broken this side length in two, this side length in two, and this side length in two. So this larger triangle here is similar to this smaller triangle in here. That means that, because the proportions are the same, this length has been halved, this length has been halved relative to the larger triangle. So the length of this hypotenuse is going to be half of the length of the overall shape, which means that this length must be equal. Because they're similar triangles, we can see that we've halved these two lengths. That means that the third length must be halved. That means that all of these angles must be the same. Does that angle come in there? No. But we also can see that this angle is actually, this triangle is congruent with this triangle. So this must be here, because again, we have this side and this side are the same as this side and this side. So we have, and we have our right angle. So we have these two triangles are congruent, which means that this length must be the same as this length must be the same as this length. So we see now that we have a parallelogram, and we can justify it to ourselves in that way. So now that we've justified that we've got a parallelogram, and it's important again to try and train ourselves for these types of things, even if we wouldn't be expected to justify it in the exam, we need to be training ourselves to spot these things and be able to justify them so that we can answer the types of questions that can regularly come up on the exams. Now, I've got a parallelogram, and I'm sure I've got a parallelogram. So I'm going to go and look for the area of a parallelogram. And I can see from page 8 in my log tables, if I have a parallelogram as such, I have a height here and a length here, the area is LH, the length of a side times its perpendicular height. So it's effectively double the area of the triangle, and we can see that because this is essentially two triangles. So it's double the area of a triangle formula. So I need to find the lengths of the sides and a height. So let's look for some of that. So I've got lengths of sides here. I know this overall length is 22. This is halved, so that's going to be a length of 11 and a length of 11. This is a length of 28. So I'm going to get 14 and 14. Well, now lo and behold, I actually have what I need, because I have a base here of 11 and I have a perpendicular height of 14. From this parallel side up to this parallel side is 14. So I now have that my area must be equal to length by height, 11 by 14. Again, where I'm getting that from is I have this length here is 14. So that means the perpendicular height coming up here is 14 for this base to base height here, for this base to base, I should say. So I have 11 by 14 is my area, which gives me 154. And it's an area, so I'm going to write in units squared to guarantee myself all my marks. The final thing to note, so that's how we break down these types of shapes when they get more complicated. We're breaking them down into shapes we recognize, like right angle triangles and parallelograms, and we build up what we know. And it's really important to take that opportunity with questions to break them down so that when we get to exam questions, we're able to break them down too. The final point that we haven't touched on much up until now is polygons. And regular polygons just means you have equal-sided shapes. So we have a regular three-sided polygon we'd call an equilateral triangle, or a regular rectangle would be, or a regular four-sided polygon is a square, or a pentagon, or a hexagon. And there's several different ways of looking at the angles in polygons, but one that I think would be most generally useful to you is anytime you've got a polygon and you want to figure out the angles in a polygon, if you draw in the center of the polygon, as we've done in here, and you draw in lines from the vertices, from the corners and vertices mean the same thing, from the vertices into the center, you will get a bunch of congruent triangles. This triangle is the same as this triangle, is the same as this triangle, this triangle is the same as this, is the same as this, is the same as this, and likewise for the 5 triangles here, and for the 6 triangles here. They are all congruent, each one in each shape. They're not congruent with each other, but they are all congruent in the same shape. Now, this is useful to us because we can figure out this angle in here. Oh, and finally, the dashed triangles are also isosceles. If you think about it, the distance from the center out to each of the vertices for a symmetric shape like our polygons is going to be the same. So this length here is the same as this length here, it's the same as this length here. Now, those facts allow us to find out basically any angles and any sides we want in a polygon. So again, put in the center of the polygon, draw in your dashed lines or your lines in from the centers to the vertices, to the corners, and then you're going to get your congruent isosceles triangles. And that the final thing is the angles I have marked in here. How would we figure out what they are? Well, there's more than one way to do it, but the way that I think is probably easiest for you is if you think about the fact that if we have 5 equal sides all going around our center here, we've effectively broken up our rotation into 5 equal parts. So we have gone around, when we've gone or rotated around through one of these angles, we've gone 1/5 of the way around our shape. So to find the angle, the blue angles I have marked here, I've written as theta here, is going to be 360, a complete rotation, divided by the number of sides. And again, this is coming from the fact that we have our triangle. I have rotated around 1/3 of the way when I've gone around one of my equal sides, and then another third, and then another third brings me back to my original position. So to find the angle at the center of a polygon, divide 360 by the number of sides in that shape. And combining that with what you know about the fact that you break your shape up into equal parts with your congruent isosceles triangles, that will give you enough tools to solve any type of problem that they could ask you with polygons. And that is what we need for shapes and areas for now.